Hello, I'm the movable Mr. Daycock, and today I'm going to be teaching you about finding sine, cosine and tangent of angles other than angles between 0 and 90 degrees. So let's first of all, think about what sine, tangent and cosine mean. So imagine I have a right angled triangle and I had it as the case that sine of theta, where my theta is my angle here, is equal to, and we'll label these sides, and if this is theta, this side is the opposite side, this side is the adjacent side, and this side up here is the hypotenuse. Of course, the hypotenuse is always opposite right angle and doesn't change depending on where theta is. In that case, sine of theta is the ratio between the length of the opposite side divided by the length of the hypotenuse. Cosine of theta is a very similar thing, which is equal to the length of the adjacent side divided by the hypotenuse. And tangent of theta, tan of theta, is equal to the ratio between the opposite and the adjacent. And these are our definitions. But as such, they only make sense between 0 and 90 degrees. So what we want to do is be able to extend these definitions beyond that. Because if I have something greater than 90 degrees, I don't have a triangle. Yeah? If this theta is all the way over here, then there's no way to produce a right angle triangle in the place that I want it to be. With the place where I want the right angle, it stops being a triangle. So we need some way of extending this idea. And the trick is this. What we want to do is we define a triangle such that the hypotenuse is always 1. So we pick our right angle triangle and it's going to be 1. And then we've got this side which I'll call y and this side I'll call x. And now, if we know that our hypotenuse is 1, is exactly 1, well that means that sine of theta, with theta still being in the same place, is in fact just y over 1. But y divided by 1 is just y. So in this triangle, this here is actually sine theta itself. And similarly, cosine theta is going to be equal to x over 1, which is of course just x. Because if I divide by 1, nothing gets changed, nothing changes. Whenever I divide by 1, I get the same answer back. So I get cosine of theta here. And so in fact, if I define this triangle with a hypotenuse of 1, the side lengths of my triangle are sine theta and cosine theta. So my triangle, in fact, looks like this. Still have theta in the same place, but here we have sine theta, and here we have cosine theta, and here we have just 1. And we also get an interesting fact that if we define the triangle like this, well, tangent is the opposite over the adjacent, so tan of theta now becomes, rather than being opposite over adjacent, it becomes sine of theta divided by cosine of theta. And this here, this is a very important rule. And in fact, it turns out that that remains true even when you haven't got a hypotenuse of 1. So this here, very important. I don't know why I put P. Important starts with an I. Okay, so how does this help us? Well, it turns out something very, very interesting occurs. If we think about all of the triangles that have a hypotenuse of 1, and I were to draw them, well, one looks like this. Let's say I had it as a lower angle. So let's say I had this triangle here. Well, it's going to go out a bit further this way because it's going to be turned down. It's going to be brought down a little bit. And so it can go out further, but not as high. Or perhaps I had a larger angle, in which case it would not go quite as far to the right, but would go a little bit higher. And if we kept doing this, if we go, oh, well, what about if it was 1 here and brought it down, 1 here, brought it down, it turns out that we get a perfect circle. A perfect circle of radius 1. And so all of these triangles with a hypotenuse of 1 fit perfectly inside a circle of radius 1. And that shouldn't be too surprising, because what we're saying is, well, what if we think about all the points which are exactly the same distance, are exactly the distance of 1 away from a particular center point? And so what we can do is use a circle. And we can use it on a graph like this. So this here is a circle of radius 1. And if I were to go from here to here, this here is a triangle with an angle of exactly 30 degrees. And this allows us to read off some information just immediately. So this side, because this is a hypotenuse of length 1, this tells us that this side here isn't just the opposite side, it is in fact exactly sine of theta. And in this case, sine of theta is 30 degrees. And if we read it off the graph, well, we can see that that is 1/2. Equally, down here, we can say that this is cosine of theta. But in fact, it's exactly cosine of 30 degrees, this length along the bottom here. And it turns out in this case this is going to be √3/2. You can't just read that off the graph, but that is the value it's going to work out as. And this remains true. It doesn't matter how big I make theta, it's still going to be the points on this circle. In fact, notice this here is in fact the coordinates of this point. This is 1/2. Oh, sorry, wrong way around. This is the point √3/2, 1/2. And if I go up here, the points here, the x and y values, are going to be my cosine and sine. So this is going to be our new definition. Cosine theta and sine theta are going to be the x and y coordinates on this unit circle. The x and y coordinates you get at any given angle. And that means that if I take a point here and take an angle anti-clockwise, I can now find sine and cosine of angles bigger than 90 degrees. Because here, let's say this angle here, this is an angle of 150 degrees, and I can read this off here, well, it's an exact mirror of this one over here. So in fact, what's going to happen here is my sine of 150 degrees, well, the point here, this point is still 1/2. But what about the cosine? Well, the cosine is exactly the same length, but it's going negative. And that's so important, it's going negative. And so this is going to end up as minus √3/2. It's exactly the same, but negative. And using this, we can find sine and cosine of absolutely any angle at all. So cosine of 150 is negative √3/2. And sine of 150 is exactly the same as sine of 30, which is a half. But let's say I was going to take an angle that was all the way down here. Well, then suddenly my sine would become negative as well as my cosine. And lastly, our tangent is going to be defined in the same way we said over here. We're going to say tangent is sine theta divided by cosine theta. So tan of theta is going to be defined as the x over the y, the y divided by the x. So just like we've got here, our cosine is defined as x, our sine is defined as y, and our tangent is defined as y over x. And now we've got a definition for every single trigonometric ratio. We just need to be able to use, and now we can use a circle to work it out. But before that, we do need to know some of these key values. So this is worth taking a note on. If you don't know them, let's get these down. These are very, very important. These are known values between 0 and 90. So sine of 0 degrees is 0. Sine of 30 degrees is 1/2. Always, absolutely always. Sine of 45 degrees is √2 over 2. Sine of 60 degrees is √3 over 2. And sine of 90 degrees is equal to 1. Always. So those are your values for sine. Let's go for cosine. Cosine of 0 degrees is 1. Cosine of 30 degrees is √3 over 2. Cosine of 45 degrees is equal to √2 over 2. Cosine of 60 degrees is equal to √3 over 2. Nope, equal to 1/2. And cosine of 90 degrees is equal to 0. These are our known values for this particular ratio, these particular areas. Tan, a little bit more awkward, but only at the end. Tan of, well, I mean, I don't even need to write down the tan because it's actually always just going to be the sine divided by the cosine. So tan of 0 degrees is going to be equal to 0 over 1, which is 0. Tan of 30 degrees, well, it's going to be 1/2 divided by √3 over 2, and that turns out to be 1 over √3, or √3 over 3 is another way of writing it. Tan of 45 degrees, well, it's going to be √2 over 2 divided by √2 over 2. So it's something divided by itself, so in fact it just works out as 1. Tan of 60 degrees is equal to, in this case it's the same as the one before, but flipped around, so it actually ends up as just √3. Tan of 60 degrees is √3. And tan of 90 degrees, this is where it goes a little bit wrong, we get 1 over 0, which is not a valid number in the system we're dealing with. So this has no answer. Okay, so you need to know those. If you don't know them, make sure you do before we go on to the next part. Okay. So let's have a look at this. Calculate sine of 135 degrees. Now sine of 135 degrees is going to be here. Remember, we take the angles, not quite there, we take the angles anti-clockwise, and this is our angle of 135 degrees. Now how do I know what these points are? How do I know what the x and y value of those points are? Well, what I'm going to do is I'm going to consider the mirror of it. And the mirror of it is going to be exactly 45 degrees. How do I know it's 45 degrees? Well, I have to ask myself what this bit is. And that is 180 subtract 135, which is our 45 degrees. So this here is 45 degrees, and therefore my mirror must also be 45 degrees. And now, well, I need to know what these points are. Well, this point is sine of 45, so cosine of 45, sine of 45, which is going to work out as, just as we, from our known values, root 2 over 2, root 2 over 2. But we just want the sine one, and we want its mirror over here. And if we notice over here, it remains positive, so sine of 135 degrees is root 2 over 2. It's exactly the same as sine of 45. Okay, let's look at cosine of negative 30 degrees. Well, if I'm going clockwise, if I always measure my angles this way, then negative 30 is when I'm measuring it sort of the wrong way. So my angle is here. And therefore my mirror is going to be exactly the mirror one up here. So now cosine is my x value. So my x value here is root 3 over 2, and my y value is 1/2. But in the mirror, because now we're reflecting in the x-axis, well, the x value actually remains the same, and the y value ends up negative. So we can say that cosine of negative 30 is in fact exactly the same as cosine of 30, which is root 3 over 2. Whereas sine of negative 30 would have been negative 1/2, because it's actually the y value has gone negative in this reflection. What about cosine of 330 degrees? We'll have to go all the way around, but in fact, 330 degrees is exactly the same as negative 30. And in fact, I could go, so this is root 3 over 2 again. And I could go further. I could say, what's cosine of, what if I went round twice, all the way around, and then all the way around again? So 360 plus my 330, so cosine of 690 degrees, well, that's going to be the same again. It's going to give me exact same values because we're defining them as the x and y values of these points. And then lastly, what's tan of 120? Let's clear this off. This is a bit of a mess now. Tan of 120, it's going to go all the way round to here. This is my angle here. And my reflection point is here. So this is tan. This angle here is 60 degrees. And again, I know that because this angle here has to work out at 60 degrees if this is 120 degrees. And so now what are my x and y values here? On my x value and y value, my x value is exactly 1/2 because I'm dealing with my x value is my cosine of 60 degrees. My y value is going to be sine of 60 degrees, which we know is root 3 over 2. And that tells us that this value up here is going to be sine over cosine, root 3 over 2 over 1/2, which we actually already know was root 3. And now, what about our 120? So that's our tan of 60 degrees, which you do have written down, hopefully, is root 3. What about our tan of 120? Well, we're going to calculate it in exactly the same way, except that when we're calculating this, our cosine value, our x value, must be negative. So it's going to be root 3 over 2 over negative a half, which is going to give us exactly the same answer, only tan 120 degrees is going to be negative root 3. Okay, so now that was a little bit complicated. I'm going to bring it back now and show you a very simple method. And if you were to try this out, when you try that out with lots and lots of different angles, you'd start noticing this pattern. And that is that all of the ratios, ooh, that went a bit funny there, all of the ratios are positive here. All of the ratios are positive. Ooh, sorry, it's slowing down a bit. All of my trigonometric ratios are positive in this, what we call the first quadrant. And if we keep going, remember we count it anti-clockwise, this is the second quadrant. And what you would find is that because in the second quadrant we're still going up, but we're now going left, sine remains positive, so sine is positive here, but cosine and tangent end up negative. So this over here is sine positive. Here is our third quadrant. You'll find over here that sine, we're going both down and left, so they're both sine and cosine are negative, but if I do a negative divided by a negative, that actually ends up positive. So here, this is where tan ends up as positive. And lastly here, we're going right, just like originally in our fourth quadrant, and so it turns out that cosine is positive here. And this is key. These, all you need to do is find your reflection angle, find what angle you're dealing with. If I say I want this angle here, well, if I want this angle, of course, the angle in green, so I look at the angle in red and consider what that would be. And what you do is you actually get this little bow tie effect here, where you're trying to deal with what are the angles in this bow tie from the angle that's turned. So if I wanted this angle here, it would be the full turn there, and then I'll just ask myself, what's this angle here? The bow tie equivalent angle, the reflected angle. And then once you know that, you just ask yourself, well, I know what my value of tan is here, so it must still be positive. I know what my value of tan is here, so it must still be positive. Or maybe I'll be asking myself, well, what about my value of tan here? Well, I know that sine is positive here, therefore tan isn't. Therefore, my value here is my bow tie value, but negative. Okay, now that's potentially a little bit confusing at this point. If you are struggling here, it is worth going back to earlier in the video and thinking about what's going on. As just a quick demonstration, let's work out what tan of 135 degrees is. So tan of 135 degrees, 135 is going to take us to here. Slightly off on my diagram actually, but this is going to be 45. So my bow tie angle, as it were, is 45 degrees. Tan of 45 degrees is equal to 1. Here, in this quadrant here, sine is positive, and therefore tan is negative. And that tells me that tan of 135 degrees is the same as tan of 45, but because tan is negative in the quadrant we're dealing with, it's negative 1. And that's all there is to it. And lastly, before I go, there is one nice quick way of remembering this. Sometimes it's called a cast diagram, C-A-S-T. Cast diagram. Okay, thank you very much for watching, and I'll see you in the next video.